Welcome. In this video, we'll be taking a look at how to predict products of composition and decomposition reactions, but this is kind of part two. We're going to deal with tricky situations. We've already should have, by this point in time, know how to do basic problems using your blue cheat sheet, which has the general patterns for how to predict what the products are. But there are a few cases where you have some things that are a little tricky. They're not normal ionic compounds. So here's an example of your blue cheat sheet that you do get to use on tests and quizzes, and it's a breakdown of our composition and decomposition reactions. And we should know how to do some of these standard ones. And number 1 and 2 give us pretty standard results, and 4 and so forth. But there are some cases where we get compounds that are not classic ionic compounds, and those can be a little bit tricky. For example, if you have a synthesis number 3, one of the products that we end up with is a non-metallic oxide, and that is it is not an ionic compound. So sometimes writing the formula for that one can be a little bit tricky. Notice we also have non-metallic oxides here in number 5. For the decomposition reactions, there are a couple cases like down here where we have non-metallic oxides in number 9 and the same thing in number 8. So notice we have asterisks by those in our sheet. That's because these ones are a little bit extra tricky. So let's show you how you can figure these guys out. The reason why these are a little bit tricky is because they are not ionic compounds, they are covalent compounds. Now, whenever we have a covalent compound, remember there's all nonmetals. And when we have an ionic compound, if I have something like salt and I want to write the formula, well, what is sodium chloride, for example? Well, there's only one option. When sodium combines with chloride, sodium's +1, chloride is -1. So the only product I can make is NaCl. There's no choice. For ionics, they're pretty straight cut like that. But for covalent compounds, they can often make several different compounds when they're covalently bonded with the same element. For example, nitrogen, when nitrogen bonds with oxygen, there are several different possibilities for what we could end up with. Sometimes when nitrogen bonds with oxygen, we get this colorless gas that we have here, which is nitrogen monoxide. But other times, depending on what the conditions are, when nitrogen bonds with oxygen, we get this brownish orangish gas, which is nitrogen dioxide. Under other conditions, we might get yet another compound with nitrogen and oxygen, dinitrogen tetroxide. So if I'm trying to combine nitrogen and oxygen and write my formula, I have a lot of choices, and I might not know which one to write. So the way we figure this out, and the reason why this is tough, is because nonmetals can have several different oxidation states or oxidation numbers when they bond. And so what does oxidation state or an oxidation number mean? Well, it's kind of similar to a charge, but it's not the same thing, because covalent things, when they bond, instead of gaining and losing electrons like an ion does, they actually share electrons. And so they don't really have charges. They didn't really gain 1 electron or lose 2 electrons. So instead of a charge, it's called an oxidation state. If it's an ionic bond, oxidation state's pretty much the same thing as charge. We'll give you some examples in a minute. But for covalent, you can think of the oxidation state as kind of a hypothetical charge on an atom when it's bonded. It's not really gaining or losing, but what's going on in the process here? So let's look at those two situations. In ionic compounds, it's really easy. Oxidation state is the same thing as a charge. So if we have calcium chloride, we can just think about that as a regular ionic compound. We know calcium has a +2 charge, and when we combine it with chloride each has a -1, so that's why we had to put those 2 chlorides together. So in this example of this formula, the calcium has a charge of +2, which means it has an oxidation number of +2. The chloride each have an oxidation number of -1 because that's what their charge is. So for ionic compounds, this is a piece of cake. Oxidation state, same thing as charge. But what about covalent compounds? Well, in this case, it can get a little bit tricky. So there's a few rules that we have to learn. You don't have to memorize all these word for word, but you get the idea of it as you look through this list. First of all, we all know that elements are neutral. So since they are neutral, all elements would have an oxidation number of 0. Even if they're a diatomic element, they're 0. Now, if you have a monatomic ion, again, here's a case where you have ions. And in that case, as we said, for ions, the oxidation number is the same as the charge. Now, other cases, if you have a nonmetal, okay, remember on our ions, they're usually the negative guys. Now, here's the big thing for you to remember. Most of our compounds, especially this unit, our nonmetal is going to be oxygen. And this is one of the most important rules for you to remember when you're dealing with oxidation states. Look for the oxygen. Oxygen gets priority to be the negative guy. It is almost always -2. So look at oxygen. All right, there's my negative guy. It's -2, and that'll help you figure out what the other stuff is. There's a couple exceptions to that. If you have a peroxide, in that case, it actually has an oxidation state of -1, but those don't pop up too often. Okay, hydrogen. Kind of a weird guy on the periodic table. He's really a nonmetal, but he's over on the metal side. So in some cases, hydrogen has an oxidation state of +1. That's when it's with a nonmetal. It kind of takes the role of a metal when it's with a nonmetal. Other cases, it has an oxidation state of -1. So hydrogen's a rough one. Fluorine, as well as all of the other ones in the group of fluorine, are either always or almost always -1. Chlorines, iodines, bromine, fluorine. Look at those guys. Automatically, you can assign those guys -1. And the big thing to remember is if you have a compound, just like we know all compounds, the charges must add up to 0. The same thing is true for oxidation numbers. If I have a compound like SO3, that is a compound, sulfur trioxide. It's neutral overall, so the oxidation numbers must always add up to 0. So those are some important things to keep in mind. Again, the biggest thing, especially this unit, is just remember, make oxygen the negative guy. He's going to be -2. That means the other guy has to be positive. Figure out what it needs to be. So take a minute and fill in this chart. There's a mix here. There's some elements, there's some ions. So go ahead and write the symbol and what you think the oxidation number is. Okay, this is a pretty straightforward chart. Copper is an element, symbol Cu. Since it is an element, oxidation numbers of all elements are 0. Chlorine, did you get the symbol right for that one? It is a janine, it's a diatomic element. So when you wrote the symbol for that element, we should have this 2 here, but it still, since it's an element, has an oxidation number of 0. Now the next one looks a lot the same, but it's chloride. The IDE ending tells me that it is the ion, so you want to make sure you have your -1 charge on that. So it's an ion with a -1 charge. That means the oxidation number is -1. Next we have nitrogen. Did you get it right? It's a gen, diatomic element, so it's N2. And again, since it is an element, oxidation number of 0. Finally, nitride. That's the ion. It's N-3. It's the ion -3, so it has an oxidation state of -3. So for simple things like this, for monatomic things, oxidation number is pretty easy, especially if they're ions. But what about if we have combinations of things that are a little more complicated? So here we have Cr2O7. This is our dichromate ion. So we're just looking at a piece of a compound. And I want to know, well, what is the oxidation number on everything here? Well, remember our rules. First, look for the O. O gets to have what charge? Hopefully you said that, -2. Okay, so that is a priority. Now, since this whole thing is not a compound, since it is an ion, instead of everything adding up to 0 here, all of our oxidation numbers must add up to -2, because that's what the overall charge on this guy is. So we can write an equation like this underneath that it must add up to -2. And remember, we said to look for oxygen first. Oxygen gets priority to be the negative guy. So since I have 7 oxygens, each with an oxidation state of -2, 7 times -2 means my total negative here is a -14. So the negative piece of this is 14. Since this whole thing has to add up to -2, I can now figure out what the positive piece has to be. In this case, my positive piece must be 12 because 12 plus a negative 14 is negative 2. So now I can figure out what the oxidation state on each chromium is. Since there are 2 of them that have to add up to positive 12, that means each chromium must have an oxidation number of plus 6. Okay, so we would say this is a plus 6. Oxide is negative 2, and because there's 2 of them and 7 of these, that adds up to negative 2. So in the case of our 3 nitrogen oxides, we can figure out what the oxidation state on the nitrogen is, and we'll see that it's not the same on all 3 of these guys. So I want to figure out what is the oxidation state on this N. Well, it's a compound, so I know the whole thing must add up to 0. Oxygen gets priority to be the negative guy, so I automatically assume a negative 2 for oxygen. So in order for this to add up to 0, that means the nitrogen has to be a plus 2. So in this case here, the nitrogen has an oxidation state of plus 2. Let's look at our nitrogen dioxide. Again, it is a compound, so that means the whole thing adds up to 0. Oxygen gets priority to be negative 2. So since I have 2 oxygens here, that means I have a negative 4 overall. Since it must add up to 0, that means in this case, the nitrogen must be plus 4. So we would say our nitrogen has an oxidation state of plus 4 in this compound. Finally, in the N2O4, again, it is a compound, so it must add up to 0. Oxygen gets priority to be negative 2, so there's 4 negative 2s. That gives me a negative 8 overall, which means my positive total must be positive 8. Now that's distributed over 2 nitrogens, so each nitrogen must be plus 4. So in both of these cases here, our nitrogen has a positive 4 charge. So that's essentially what you want to do to figure these out. So on our next page here, we have a bunch of examples. So take a minute. Now I'm going to go over these 2 first. So take a minute and do these 2 in this column, the Al2O3 and the MnO2, and then we'll go over the answers for those, and then I'll actually have you do the first column. It's actually a little bit trickier. All right, so looking at our results for this one, we have Al2O3. It is a compound, so overall, the oxidation states must add up to 0. In this case, it's actually pretty easy because this is an ionic compound. And so we really know what the charge is. The oxidation state is the charge. We know oxygen is always negative 2, and aluminum, we have that memorized as plus 3. We can double check that. There's 3 O's, negative 2, so that would add up to negative 6. 2 plus 3's, that adds up to positive 6. So yes, that one is actually pretty easy because that's a straight up ionic compound. Next we have manganese and oxygen here. And what's the charge on the manganese? Well, again, this is one of our ions on our list. So we know, again, oxygen's negative 2. And now we might not be sure what the manganese is, but we can figure it out because 2 negative 2's gives me negative 4. In order for this to add up to 0, we've got to have a positive 4, and there's only 1 manganese, so that means our oxidation state, in this case, is a plus 4. So all those schizophrenic or multiple charge ions, when we have Fe is plus 2 and when we have Fe is plus 3, when we figured out which one it is, these numbers, these charges that we've come up with, we could also say, hey, well, this is the oxidation state. Okay, so take a minute and do those 3 in the first column, and we'll see what you come up with. All right, going through these, we have N2O5, okay, dinitrogen pentoxide. It's a compound, it's got to add up to 0. Oxygen gets priority to be negative 2. There's 5 negative 2's, that gives me negative 10. That means my positive has to be positive 10. Divided by 2 nitrogens, that means my N here is plus 5. So that's the oxidation state in the first one. Jumping down to this middle one. Now it is ionic, and I know because this is ionic, I have aluminum, nitrite. I know the aluminum's plus 3. I know this nitrite overall is negative 1. But if I zoom in on the nitrite, okay, that's NO2, and it has a negative 1 charge overall, I can figure out what the charge on the N is. So just zooming in on that ion. Now in this case, it's an ion. It doesn't add up to 0. It adds up to negative 1. So O gets priority to be negative 2. 2 times that gives me negative 4, which means the positive here, now this case, I'm not adding up to 0. We want it to add up to negative 1. So that means I have to be +3 in this case. And there's only one N, so in this case, the oxidation state is +3 for my nitrogen.